Okay, hi again everybody. Professor Sebastian and our statistics class notes on page 73. All right, we're going to go ahead and reset this applet that we just worked on in the last page. And we're going to take the top left and we're going to set the sum of one roll equal to 1. All right, and then I'm going to go ahead and do 30 runs here, 5 at a time. Okay, so I'm going to go 5 runs, that's 5. Okay, notice that we had no ones come up yet, so the count on the ones is 0 right now. I'm going to do, here's 5 more is 10. This was my first one that came up. Okay, it's looks like I had 2 ones out of my 10 rolls so far. That's a proportion of about 2.2. We know that over the long run, this should be about 1/6, right, which is about 0.167. Let's keep going. 15. Took 5 more runs. No other run came up. 2 out of 15 is about 0.1333. Let's go 5 more runs to get to 20. It's creeping down there, right? About now down about 0.1, so it's below what it should be. It should be around 1/6, which is 0.167. Over the long run. So 2 out of 20. Let's see. Let's go 5 more runs. Wow, really not showing up. This one here. Okay, let's go 5 more runs. Let's do 30. Okay, so over 30 runs, we only got 2 runs. Now, over the long haul, it should be 1/6, which we should have seen about 5 ones. But again, over any 30 rolls of the die, I mean, you're not guaranteed to get 5 out of 30 or exactly 1/6. So we're under, and that's about a 0.0667 probability or 6.67% chance of getting a 1. When we really know it's about 16.7% chance or 1/6 probability. So what happened when we did that at the beginning of the graph, it just, we didn't get very many runs at first. It kind of oscillated around. It stuck around about 0.1 and has even fallen down to 0.0667. Now we're going to go ahead and take a whole bunch of runs, okay? So I'm going to go to like 3,030. I'm going to go 1,000 runs, right? And then I'm going to go to like 3,030. So I'm going to add 3,000 runs. So I'll go 1,000. Okay, it jumped up to 0.1748, which is probably a little bit more than the number of ones I should have gotten over that, over the, expectation of getting. I should have got about 0.167. So I have a little few more ones than I would have expected to get. We'll go to 2,030, still around 0.1724, and then 3,030. So I'm actually, you can see the height of the bars even more, right? This fairly uniform distribution again, but unless we go to infinity, these aren't going to all be exactly the same. We would like them to all be around 1/6 or 0.167, but right now we see 1 is at 0.1739. Anyways, what we're witnessing here is the law of large numbers. So on the middle of your page. So what we'll say is we'll take 30 runs. In part A, we're going to write down that we saw that very few ones were coming up at first. We continued to take more runs in part B until we had about 3,000. What started happening to the graph? We actually, the graph started turning fairly symmetric across the board, and we actually have a few more ones than we would expect through the theoretical probability there. And what value is the graph settling down on approaching? It settled down on approaching about 0.1739 here at 3,030. Approximately 1/6, but a little bit over. And that's the law of large numbers. If an experiment with a random outcome is repeated a large number of times, the empirical probability of an event is likely to be close to the true probability. So the larger the number of repetitions, the closer together these probabilities are likely to be. That's the law of large numbers. If we could take this all the way to an infinite number of runs, we'd get 1/6, 1/6, 1/6, 1/6, 1/6, 1/6 across the board. Okay, so on this next exercise, we're going to roll 2 dice instead of 1. So I'm going to go to my options here. I'm going to edit this. And I'm going to do number size on the dice is 6. I'm going to roll 2 dice. Okay. So we're going to roll 2. I'm going to go ahead and hit compute. Okay, bring my applet over here where you can see it. Okay. Now notice that when I roll 2 dice, the smallest number I can get is a 2, right? Because when I add up the sum on the face of the dice, because I could roll a 1 on one and a 1 on the other. So the smallest number I get is a 2. The biggest number I get is 12 when I roll 6 on one and a 6 on the other. And I could get every number in between 2 and 12, including 2 and 12. So 2, 3, 4, 5, 6. Those are the numbers you can get when you roll 2 dice. So I'm going to roll a pair of dice about 3,000 times. So I'm going to roll it 1,000, 2,000, 3,000. I clicked on 1,000 runs 3 times. Okay. And notice I get a nice sort of symmetric looking distribution here. Symmetric with the mean right here in the middle at about 7. Okay. So if I check the proportion of all these events, I'm going to take the sum of the 2 dice. Let's go equal to 2. Okay. Take this 2. Notice that that sum was a proportion of 0.029. Okay, and if I take the sum equal to 3, I got a proportion of 0.0547. I'm writing this down to table at the bottom of page 73. If I took a sum equal to 4, I got 0.0827 is the proportion. How can I get a 4 with 2 dice? I can roll a 1 on one, a 3 on the other, a 2 on one, or a 2 on the other, or a 3 on the first one and 1 on the other. So there's 3 ways it can get 4. And similarly, you can think about how many ways you can get 5. So let's look at 5. So since there's more ways to get 5 than there is to get 4 than there is to get 3, you're seeing more of them come up. So let's see, this is 0.121, 0.121 to get a 5, which is, the sum of the 2 rolls adding up the face of each dice. 6, you can see that's even more than what I should have got with 5, so that's going to be 0.1407. For 7, I got 0.1643. For 8, I got 0.131. Again, I'm writing these down at the bottom of page 73. For 9, I got 0.1147. For 10, I got 0.082. For 11, I got 0.0467. And for 12, 0.0333. And if I add all those up on my calculator, I got 0.029 plus 0.0547 plus 0.827. Nope, 0.0827, sorry. 0.0827. Okay, and then plus 0.121 plus 0.1407 plus 0.1643 plus 0.131 plus 0.1147 plus 0.082 plus 0.0467 plus 0.0333. And I got 1.0001, which we'd expect as probabilities to add up to 1. So it's a little bit of round off error, but other than that, they worked as far as all adding up to 1. Okay, so what we want to do then is figure out exactly when I look at this and I say to myself, so I'm going to the next page, on page 74, what's the probability of rolling a sum that is less than 10 with 2 dice? Okay, this is the, you take the outcome. Sum of two rolls, you want that to be less than 10. So we want the less than sign strictly. Put in 10. And it added up all those probabilities. Okay? When it adds up all those probabilities, it gets 0.038. Okay, so this is 0.038. This is part D on the top of page 74. This is the probability of the event A, which is at least a sum of 10 on 2 dice. What's the probability of rolling at least a sum of 2 with 2 dice? At least a sum. Oop, I did it wrong. Probability of at least a sum. This is where I said you got to be careful with the words. At least a sum of 10 means 10 or more. So we actually want greater than or equal to 10. Got to make sure we do that. That's going to be 0.162. That's part D. 0.162. 0.162. Now what's probably at least the sum of 2? At least the sum of 2 means 2 or more. Well, that should sum up to be 1, right? So greater than or equal to 2. So sum up to be our 1.001? No, 1. They didn't round it off. They knew that should be 1. So probability of at least 1 is 1. What's the probability of rolling a sum of 1? So a sum equal to 1. Now that can't happen, right? We talked about with 2 dice, that's impossible. That's 0, of course. And let's look at the actual theoretical probabilities. So I'll go back to the notes at this point and create another video.